of functions, if we have two functions, let's say f of x and g of x, we can create a new function by taking the sum or the difference of these two functions. So we can create a new function, h of x, by either adding. Okay, so h of x could be defined as f of x plus g of x. And just in terms of notation, when you take a function and it's the sum of two other functions, you can write this f plus g of x as f plus g in a bracket of x. Okay, so those mean the same things. And with subtraction, okay, we could say h of x equals f of x minus g of x. And again, we could write that as f minus g in brackets of x. Okay. Here's a question. Is f of x plus g of x the same as g of x plus f of x? Yes. What about with subtraction? No. Okay, so with subtraction, order matters. Right? So you could have this function, or you could have another function, h of x equals g of x minus f of x. And in fact, these will be related to one another. They are negatives of each other. Okay? Just like 5 minus 2 is the negative of 2 minus 5. So we could write this way as well. G minus f of x. Okay, so some of the things that we're going to be looking at today is how do we do this? How do we write an equation for a sum or difference function? Graphically, what happens, right? How do we look at the graph of two functions and come up with a sum or difference function? And then also, what happens with things like the domain and range? Okay, that sort of thing. All right, so consider the functions. F of x equals negative 4x minus 3, and g of x equals 2x squared. Okay, so the first thing that we are going to do is determine the equation for the function h of x equals f plus g of x. Okay, so essentially f plus g of x is the same as f of x plus g of x. And now we can just sub each function in to that equation. So this f of x is negative 4x minus 3, and then plus 2x squared. Okay? And at this point, if you wanted to, you could rearrange the terms. Sometimes at this point, there's some simplification that can happen because you might have some like terms, that sort of thing. So at that point, you might do this. I'm just going to rewrite this as h of x equals 2x squared minus 4x minus 3, just because I can see that that's a quadratic, and I personally am used to writing quadratic functions in that order. Okay, so we actually already answered part B. Are these the same? Is this always true? And the answer is yes, right? For addition, order does not matter. Okay, so what we're going to do next is sketch the graphs of the individual functions, and then by making a table of values essentially, and then we're going to use those two individual graphs to try and sketch the graph of h of x. Okay, and we're just going to do so by subbing in x values. So here we want to know what's f of negative 2. So we're going to sub in a negative 2 for x. Negative 4 times negative 2 minus 3. And I believe that is 5. Is that right? I think so. Yeah. This is negative 4 times negative 1 minus 3. and that is 4 minus 3 is 1. This is negative 4 times 0 minus 3, which is negative 3. Looks like these are going down by 4, so I'm just going to write in the next two values. This one will be negative 7, and this one will be negative 11. Okay, and now I'm going to switch colors so that it's a little more clear when I'm graphing. So g of 2x squared, 2 times negative 2 squared, that's 2 times 4 is 8. And then 2 times negative 1 squared is 2 times 1 is 2. 2 times 0 squared is 0. This would be 2 times 1 squared is 2. And 2 times 2 squared, 2 times 4 is 8. Okay, now h of x is defined as the sum of f of x plus g of x. So what do you think the y value is going to be for h of negative 2? Yeah, it's 5 plus 8, right? Because essentially we're just taking parts of the function of h of x and evaluating separately and then adding. So h of x is equal to 2x squared minus 4x minus 3, right? If you think about it, the 2x squared part is that 8. And the negative 4x minus 3 is the 5. So we're just adding those together. Okay, so this is 5 plus 8, which is 13. This one is 1 plus 2, which is 3. Negative 3 plus 0 is negative 3. Negative 7, whoops, negative 7. Plus 2 is negative 5. And then negative 11 plus 8 is negative 3. Okay, so when we graph these, okay, I'll just stick with the same colors. The first one is a linear function. So let's see, negative 2, 5. And then negative 1, 1. 0, negative 3, 1, negative 7, and 2, negative 11. There we go. Okay, so there's the 1. Okay, and then the blue one is a parabola. So negative 2, 8, negative 1, 2, 0, 0. 1, 2, and 2, 8. There we go. And then the green one is a sum of the two. Okay, so negative 2, 13. Negative 1, 3. 0, negative 3. 1, negative 5. And 2, negative 3. So it looks like actually this is the new vertex at 1, negative 5 rather. Okay, so how could we use the values in the column for f of x and g of x to determine the values in the column for h of x? So we just did this actually, we just added them, right? So to get the new y value, essentially you can apply the same operation that creates the function to the two y values of that specific x point, right? Okay, now this is kind of interesting. So domain and range, let's kind of look at these one at a time. For f of x, that's the black function. What is the domain and range of that function? Yeah, x and y can be anything, right? It's linear. So x is an element of the reals, and y is an element of the reals. Okay, what about the blue one? What's the domain? Yeah, x is an element of the reals. It's a quadratic function. So in fact, the green one is also x is an element of the reals because it's also a quadratic function. What about the range, though, for g of x? Yeah, y has to be greater than or equal to 0. Okay, and what about for h of x? Right. Y has to be greater than or equal to -5. Okay, so we're going to talk a little bit more about domain and range of originals versus the sum or difference function in a little bit, and specifically the range. Okay, what I'll tell you, it's not quite as clear in this example because the domain for all of them is that x can be anything. But the domain of the sum or difference function is going to be sort of the more limited domain of the two individual functions. Now, it's not super clear in this example because none of the functions were limited in their domain. But we will see that in some other examples, right? So for example, if one of the functions is x can be anything, but the other function is x has to be greater than or equal to 0, as soon as you add them, the domain of the sum would be the more limiting one. X has to be greater than or equal to 0. Okay? Now, everything sort of stems from the domain, and then you have to kind of look at the equation or the graph to figure out what the range is going to be. So the range is not quite as predictable as the domain, but again, we'll look more at this a little bit later on. Okay, so determine the values of f of -4, g of -4, and h of -4. So for f of -4, that's -4 times -4 minus 3, which is what? 16 minus 3 is 13. G of -4 is 2 times -4 squared. So that's 16, 2 times 16 is 32. Now, however you sort of evaluate h of -4, you should get the same answer. You can either think of it in terms of the actual equation, h of x equals 2x squared minus 4x minus 3. So if I plug a -2 in there, sorry, not -2, -4, then I will get, let's see, that's 2 times 16 is 32, and then plus 16 minus 3, which is 45. Okay, so you can do it that way, or you can just think h of -4 should be f of -4 plus g of -4, and we just evaluated those. So f of -4 was 13, and g of -4 was 32. And when you add those together, you get 45. Okay, so it shouldn't matter sort of how you evaluate that. You should get the same answer no matter what. Okay. All right, so let's look at another example. We're going to do a difference of functions this time. So consider the functions f of x equals absolute value of x and g of x equals x minus 5. And now we're going to first determine an equation for the function h of x equals f minus g of x. So what would that equation be in terms of x? F minus g of x. Yeah, so f of x, if you want to do it this way first, you can. Split it up like this. And then that's absolute value of x minus, now here's where you have to be careful, okay? Because we're subtracting the entire function. So we have to put brackets around this. And so when we distribute those, the negative sign in, h of x is going to be absolute value of x minus x plus 5. Okay? Okay, so let's start getting some y values, some points. So we're going to sub in these x values. H of negative 2 is going to be the absolute value of negative 2 minus x minus negative 2 plus 5. So what is the value of that? Yeah, it's 9. So this part's 2, and then plus another 2 is 4, plus 5 is 9. Okay? Here, this will be the absolute value of negative 1 minus negative 1 plus 5. 7, yeah, because it's 1 plus 5 is 7. Okay, and then here, absolute value of 0 minus 0 plus 5, that's just 5. Okay, and then when x is 1, absolute value of 1 minus 1 plus 5. What's that? It's 5, yeah. Okay, here, absolute value of 2 minus 2 plus 5. Yeah. Okay, and the reason that this happens is essentially when x is greater than or equal to 0, the absolute value of x equals x. And so essentially, for all of these guys, you don't even need those absolute value signs there. They're not going to change anything. So we're just basically, when x is greater than 0, going x minus x plus 5. Well, x minus x is 0 plus 5. So anytime x is greater than or equal to 0, the value of this function is just going to be 5. Okay? When x is less than 0, though, right, this actually becomes positive. And then when we subtract that same negative value, that becomes positive again. Okay? And that's because this absolute value function is called a piecewise function, right? We can't actually write it out in terms of x unless we split it into two pieces. It's two linear functions, right? It looks like this. So when x is greater than or equal to 0, the absolute value of x equals x. It's like the function y equals x, right? But here, the absolute value of x equals negative x. Okay? It is difficult to predict that this is going to happen, though. So for some of these types of functions, just make a table of values. And as long as you plug things into your table correctly, you should get an accurate graph. Okay, so this is going to be, let's see, negative 2, 9, negative 1, 7, 0, 5, and then the rest of these are all 5. Okay, so in one way it makes sense in that one of the functions starts as a piecewise function, and so the sum or difference should also end up being a piecewise function, but it's not totally intuitive how that happens, okay? Because, on the right-hand side anyway, when x is greater than or equal to 0, this side is just constant. So it's not like the v, this v over here, like we get a transformation of that exactly. Okay? But it is still a piecewise function. Okay, so state the domain range of f of x, g of x, and h of x. Okay, so all three of these have a domain where x is an element of the reals. You could put any x value into all three of these functions. You can put any x value into an absolute value function. You could put any x value into a linear function. And because both of these are are elements of the reals, when you add or subtract them, you could put any x value into that as well. Okay, so the range, if we look at the range of f of x, Okay, what's the range of y equals the absolute value of x? Yeah, greater than or equal to 0, exactly. What about g of x? G of x was x minus 5. Yeah, it's linear. Y is an element of the real numbers. And then for h of x, what's the range of that? Yeah.
Y must be greater than or equal to 5.
That's correct. Y is greater than or equal to 5. Okay, so is the function f of x minus, or f minus g of x equal to g minus f of x? No. Okay, and actually if you look at this function, this guy is the absolute value of x minus x plus 5. This one would be x minus 5 minus the absolute value of x. Okay, now if you rearrange the terms here, this is negative absolute value of x plus x minus 5. And if I take a negative sign out, if I factor a negative sign out, then it is in fact the negative of the first one that we figured out. Okay, so what it would actually look like is it would be a reflection in the x-axis. It's the negative of the other function, so we would reflect it in the x-axis. Okay, so in summary, to add or subtract two functions, okay, we are essentially just going to add or subtract the original functions and simplify if we can. I feel like that sentence, I could have phrased that better, but I think you guys know what I mean. Okay. The important piece is the domain and range. So the domain is the most limiting domain from each piece. And the range really actually depends. So for the range, you have to either work out the range algebraically or look at the graph. It's not, we can't make a generalization based on the ranges of the original as to how the range of the new function is going to behave, right? We saw with this one over here that the two original ranges where y is an element of the reals and y is greater than or equal to 0. And then we got this new range of y is greater than or equal to -5. Okay? So that's not super predictable based on the two original ranges. So you really have to either look at it graphically, or with this one, depending on the type of function, you could work it out algebraically as well. For example, this one is quadratic. So if you really needed to work out the range algebraically, you'd have to actually complete the square to put it into vertex form and get the range that way, right? So it is doable depending on the type of function, but we can't make a generalization around it. Okay, so the range sort of depends on, I should say it sort of depends on the combination, on how the functions are combined. So the important piece is look to the graph. Like we can't even say, for example, that if both ranges are y or elements of the real numbers, necessarily that the new range will be that as well. Because if, for example, you took one function to be y equals x and the other function to be y equals negative x, when you add them together, you get y equals 0, which just has a range of 0, right? So there's no generalization that we can make here. So you have to treat it on a sort of individual basis. Okay. Let's do some examples, though, where we focus in on the domain and where we may not have a domain for all of the parts, where x is an element of the real numbers. Okay. So we have these two functions, let f of x equal x plus 1, g of x equals the square root of x minus 4. So first we're going to write the equation of the combined function and then determine the domain without the use of a calculator. Okay, so if we were looking at f plus g of x, we would be adding these two functions. So we would have x plus 1 plus the square root of x minus 4. Okay, so which piece of this function do you think we need to look at to figure out the domain? The square root, yeah, because square roots are where we have restrictions as to what we can put inside, right? We need to make sure that the radicand is positive. So we need this condition. Okay, and that works out to be a domain of x is greater than or equal to 4. Okay, so the function is only defined where the more limited part is defined. Okay, and with this guy, it's going to be the same sort of idea if we're subtracting functions. Just make sure with subtraction that you put the second one in brackets, that you subtract all parts of it. Square root of x minus 4, I actually kind of like to put them both in brackets so that I don't make any mistakes, minus x minus 1. So that is square root of x minus 4 minus x plus 1. Oh, yeah, right. It would help if I copied it down correctly. There we go. Okay. Again, though, with this domain, we need to look to the piece that's under the radical sign. And so the domain for this second part is going to be the same as the domain for the first part, in that x has to be greater than or equal to 4. That's the only piece that matters. Okay. Now, if you had two radicals in there that both had restricted domains, you'd have to compare the two domains and take the one that's more limiting. Okay? All right, so what we are going to do now is take a look at a couple of graphs and sketch the combined function given the graphs that we see. And essentially, the key pieces here are that the x values don't change, but we're going to look at the y values and combine them in the same way that the function has been created, right? So to get h of x here, we have to add the y values, because h of x is f of x plus g of x. Okay, so what I like to do is find y values where I can see both y values for the same x value. So I'm not going to worry when x is negative 1, because on g of x I can see that it's equal to 2. I can't see that value for f of x. I could work it out algebraically, but I probably have enough information from other points in the graph that I don't have to do that. Okay, so let's see. When x equals 0, one of the values is 0, and the other one is at negative 5. So what's the sum of 0 plus negative 5? Negative 5, yeah, so I'll do that one in green. Okay, and then when x is 1, one of them is negative 2, the other one's also negative 2. What's the sum of negative 2 plus negative 2? Negative 4, yes. You got to be careful if you're adding or subtracting, right? And then, let's see, here, when x is 2, f of x is 1, and g of x is negative 4. So what's 1 plus negative 4? Negative 3. Yeah, so you can kind of see, okay, it looks like this is going to be linear. And we'll do one more. When x is 3, f of x is 4, and g of x is negative 6. So 4 plus negative 6 is negative 2. And we can see that this is going to make this linear function. Okay, and if you were to actually write out an equation for g of x and for f of x, which we could do because we can see the slope and the y-intercept of each, and we actually add those together, we should get the equation of this green graph. It looks like here the slope is 1 and the y-intercept is negative 5. So this is x minus 5. Okay? Okay. So far, so good? All right, let's look at this one. Now, one other thing that you could do, and sometimes I tell myself that I really should do this just so that I don't make mistakes, is instead of just doing this on the graph automatically, you could actually create a little table of values and then do the subtraction within the table of values. Because I was actually looking through the completed notes today, and I realized that on this question I made a mistake in the completed notes because I think I added instead of subtracted, right? So let's maybe do that with this one. I'm just going to make a really quick table of values where what I want to track is what's the value of x, what's the value of f of x, what's the value of g of x, and then h of x is f minus g of x. So I want to know that as well, f minus g of x. So I'm going to be subtracting these two columns. Okay, so let's see. G of x is this one over here. Okay, so let's see. I'm going to keep track of maybe not all of, you know what? I'm going to look at the parabola first because there I have actual values that I can, I want to put in values that are rational, right? So let's see, negative 4. There's one here, negative 2. Negative 1 I can see is at a half. 0, and then maybe I'll do 1, 2, and 4. Okay, you don't necessarily need every x value when you're creating this table of values, but I specifically picked these. The reason why I didn't pick negative 3, although I suppose I could have, it looks like that's about 4.5. I just want to pick values where I'm going to have y values that are rational. I don't think it would have been a big deal if I had picked negative 3 and 3 as well in this case. But anyway, this should give me enough. So when x is negative 4, y is at 8. I'm doing f of x first, right? So that's the parabola. When x is negative 2, y is at 2. This is at a half. 0, and then it's symmetrical. 0.5, 2, 8. Okay, and for g of x, when x is at negative 4, y is at 4. And then negative 2, 2. Negative 1, 1. 0, and then again there's like symmetry here. So 1, 2, and 4. Okay, so when I subtract them, 8 minus 4 is 4. 2 minus 2 is 0. 0.5 minus 1 is negative 0.5. 0 minus 0 is 0. Yes? It's going to be a little weird. 0.5 minus 1 is 0.5. 2 minus 2 is 0. And 8 minus 4 is 4. Oh, sorry, this is negative. negative 0.5. Okay, so now I'm going to plot these guys. It's going to be weird. Yeah, it's going to be like a sort of part of a heart. Okay, so let's see. -4, -4. -2, 0. -1, negative 0.5. 0, 0. 1, negative 0.5. 2, 0, and 4, 4. So it's going to kind of look like this. It's kind of odd and honestly not super predictable. I feel like for me to graph that, I really have to go through it point by point to see what it's going to look like. Okay? But hopefully it's not like too terrible a process. Okay. Here's another one. So we are going to use the graphs that are given to us of f of x and g of x to evaluate these values, essentially. Okay? So first, g of x is this absolute value function, and f of x looks like it's the radical function. Okay? So first we want to know what's g of -4. G of -4, 5. Okay, what about f of 0? 2. F plus g of -5. Yeah, I find the addition ones easier to do in my head than the subtraction, because I think I'm just less likely to make mistakes. But essentially, we're just adding the two y values, right? So one of them is at 3, and the other one is at 6. So this is going to be 9. Okay, f minus g of 3. So yeah, like f of 3 minus g of 3. So f of 3 is 1. G of 3 is 2. So 1 minus 2, that's -1. Okay, and then g minus f of 4. So that's what? 3 minus 0? Yeah. Okay. And then f plus g of 5. Undefined. Yes. This is undefined because f of x is not defined for x equals 5. Right? 5 is not within the domain of f of x. Okay. So far, so good? Okay. All right, so let's take a look at this question. Here, essentially what we're doing is looking at sum and difference functions through the lens of transformations. So let f of x equal absolute value of x, and g of x equal 5. Okay, so first, here's what we want to do. Write an equation in terms of x for each of the following. So we're going to write out an equation. And then we want to talk about how we could actually get each of those functions just by applying transformations to f of x equals absolute value of x. Okay, so let's start by doing these sum and differences first. So what would this function be? Yeah.
Absolute value of x equals 5.
Right. Okay, what about f of x minus g of x? Subtract 5, right? So absolute value of x minus 5. And then what about g of x minus f of x? Right. Okay? Okay, so for number 1 over here, how can we get that same function just by applying a transformation or several transformations to f of x equals absolute value of x? Yeah. Translate up 5 units. Okay, what about for 2, for the second one? Translate down 5 units. Okay, what about the third one? Yeah, okay, so here you want to just maybe reorder the terms here and think of this as negative absolute value of x plus 5. Yeah, so this is a vertical reflection in the x-axis, and then we're translating up 5 units. Okay. And then last question of the day. A communications company manufactures a mobile phone for $25 per unit plus a fixed operating cost of $45,000. The mobile phones are sold for $100 per unit. Okay, so the first thing we want to do here is determine a function to represent the cost of producing n units. How much does it cost this manufacturer to produce n phones? And it actually may help you to read through the whole question to figure out how to do this. So we want to come up with a function for the cost, and then we want to come up with a function for the revenue, and then we want to come up with a function for the profit. Because there's lots of information that's given to us in these first few sentences, and not all of it is going to apply to every single piece of this. Okay? So which parts apply to the cost of the company of producing the phones? Yeah. Shh. Yeah, it's this fixed operating cost, right? That maybe pays for their machinery, it pays for their rent, that sort of thing, business license, that sort of thing. And then I suppose the materials for each phone is $25 a piece. So C of n would be 25n plus 45,000. Okay, that's what it costs them to produce these. Okay, what about the revenue? How much revenue are they getting from these phones? What's that? 75. Not quite. Revenue is the total amount of money that you take in. Yep. Yeah. R of n is 100n. That's the amount of money that they're going to take in from customers. Okay, so now let's talk about the profit. If you have cost and revenue, how do you get profit from your cost and your revenue? Yeah, so profit is your revenue minus your costs. Okay, so if I buy a t-shirt for $2 and sell it to you for $8, my profit is $6 because I got to subtract my cost. So your profit is your revenue minus your cost. So P of n is R of n minus C of n, which is 100n minus 25n plus 45,000. So that is, I'll just write it up here, 75n minus 45,000. Okay? Okay. Break-even point. What is the break-even point for the manufacturer? What does it mean to break even? Yeah, you don't make anything, but you don't lose anything. So break-even is when your profit equals 0. Okay, so we're going to sub a 0 in for P of n. Okay, and then we can add 45,000 to both sides. Okay, divide by 75. What is that? I don't know.
600.
600? Okay, so they have to sell 600 phones to break even. Do you guys know, this is just sort of a side note, but why we probably use the letter N here as opposed to X? Yeah. Any? Yeah. So typically when our data is discrete, and specifically when discrete counting numbers or whole numbers, 0, 1, 2, 3, 4, 5, we often use the letter N for that variable instead of the variable X. And in fact, if you look at your graphing calculator, I don't know if it does it on the Casios, but on the TI, there are 4 letters that are listed for variables, which are just the different, or letters or symbols, I should say. Those are the different letters or symbols that are commonly used, and N is one of them. And that's what we typically use when we're counting a number of items, and that has to be discrete. Okay? All right. So I'm going to stop there for today, and tomorrow I think we're talking about product and quotient of these things.